Lecture 1, Inventory Control with Known Demand, Chapter 4 of the textbook, and this is the last part of this lecture. Another extension that we can have for the basic EOQ model is assuming multiple products. So when we have multiple products and all products are completely independent, I mean, there is no relationship between the products, then yeah, we can consider each product individually and go with EOQ model, and that's it. But usually they are not independent. I mean, there are some sort of relationships between the products, like having limited total budget on purchasing the goods. So we have several goods, but our total budget is limited for purchasing all goods. Or we may have limited inventory space in our store, so it affects on the quantity of the goods, right? So because of these two, let's say, restrictions, we can say that the multiple products are independent. So we need to consider the case of the multiple products here. Okay. Let's have an example here. Let's assume that we do have three products, and the total budget for purchasing the goods is $30,000. So our total budget is limited to $30,000. Okay, and here we do have three items. I mean, three products. Okay, and as you see here, we have the data here: lambda j demand rate, annual demand rate for each item. We do have the variable cost CJ, unit purchase price, for each item, and also setup cost KJ for each item as well. And the interest rate for holding cost is 25%. Okay, so let's assume that the goods are independent. So if we consider the individual case and obtain the EOQ for each product, each item separately and individually from the others, then we will have these values for EOQ. Okay. Now we do have the quantities. I mean, the optimal order quantities. If we multiply these by their associated variable cost, then we can obtain the total purchase cost here, which becomes $35,835. And as you see here, it's greater than $30,000 our budget. So it's infeasible, right? We can't order the product with their EOQ value. Okay, so it's because it's infeasible. In general, when we have budget or space limitation, we can have two cases. The first one is EOQs are feasible. I mean, the individually obtained EOQs are feasible. So here the constraint is inactive. For the budget, the total purchase price is less than or equal to our budget. So in this case, the obtained individual EOQs are optimal for the multiple product case as well because they are feasible. So that's it. And the second case is EOQs are infeasible, like our example. So here the constraint is active, and for the budget, the total purchase cost is greater than our budget. So in this case, we need to modify the quantities in order to be feasible as well by our constraint. So in order to modify the quantities, we assume here one assumption that C1 over H1 equals C2 over H2 up to Cn over Hn, which means that the interest rate I is equal for all products. And it makes sense. I mean, it's not a very bad assumption here. So the optimal solution for multiple product case, Q star I, becomes this: M times EOQI. So we obtain a multiplier M here, and then we multiply that multiplier by EOQs, I mean individually obtained EOQs, then it will obtain the Q star as optimal solution for multiple product case. And M comes from this equation. C here is our budget divided by the total purchase cost, and M is a number less than 1. So here we are going to modify the EOQs by this multiplier, and then that will be the optimal solution for the multiple product case. Okay. With the same manner as a limited budget for space constraint, we can modify the EOQs in order to be feasible by that constraint and be the optimal solution for the case of multiple product. And our simplifying assumption here is this: W1 over H1 equal to W2 over H2 up to Wn over Hn. So this means that the space consumed by each product is proportional to its value. So it's somehow a restrictive assumption, right? Yeah, comparing to the budget constraint, here our assumption is more restrictive. So, but by having this assumption, we can go with the same manner as budget constraint to modify the EOQs to be feasible solution for the multiple product case. So at the end, the optimal solution for our multiple product case. Okay. So as a last model of this chapter or lecture 1, let's consider the EPQ model with multiple products. So here we assume that we do have a single machine and we have n products, and all n products can be produced by that single machine. Okay, so here we need to assume this assumption that lambda as that sum over j on lambda j over pj should be less than or equal to 1. So this assumption is necessary because it guarantees that the problem is feasible. I mean, we can satisfy all demands. Okay, and also we assume the rotation cycle policy here. This means that at each cycle we have exactly one setup for each product, and we will produce some quantity for each product at each production cycle. Okay. So at first we may think that the optimal solution could be obtaining the individual EPQ for each good, and then produce all the items in sequence with the obtained lot sizes, right, with this equation. So one problem that could be occur in this approach, it's likely to have some items that Qj for those ones are not large enough to meet the demand during the production cycle. Yeah, I mean, the production cycle is the period that we produce all the quantities for all items. So for some goods, the QJ, EPQ, may not be large enough to satisfy the demand over this period as the cycle time. So that's a problem. So we can't go with this approach. Okay. So in order to have an appropriate approach here, we assume that the production cycle or the cycle is T here. Okay. So here we can say that if we have a T, then we do have a demand rate for each item, each product. So lambda j times T could be Qj. Okay, so if we produce Qj by this equation, lambda j times T at each cycle, then we will be sure that we have enough inventory, enough production and enough inventory to satisfy all demands during the cycle time. So by this interpretation, now the optimization problem turns to obtain T star instead of Q star. So if we obtain T star, and then by having that, we can easily obtain Qj star as well by multiplying lambda j by T star. Okay. So in the objective function, average cost function for the inventory system, we do have this equation, right? So we know that Qj divided by lambda j is T. The cycle time is Qj over lambda j. So in this equation, if we replace Qj over lambda j by T, then we will have this function. So as you see here, our objective function or average cost function now is in terms of T instead of Q. Okay, so now if we take the first derivative of this function with respect to t and set it to be 0, then we can obtain t star. So t star could be this, right? So now we have t star, and if we multiply, so if we multiply lambda j by t star, then we can obtain q star j for product j. Okay. If the setup times are significant, I mean, changing the setup of the line or the machine to produce a different product, it, 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 it takes time, right? But if this time is negligible, we will, I mean, ignore the setup time in our model. But if it's significant and we can't ignore that, so we need to consider the setup times here as well. So let's assume that Sj be the setup time for producing item j. Then here the total time, I mean, Sj plus Qj over Pj. So yeah, here Qj over Pj is the production time for producing Qj item of item j, right? So, and Sj is the setup time for that item. So if we add up all these times, so this time should be less than or equal to our cycle t, right? So so this means that we should have this inequality, and then by having that, we see that t and the cycle should be greater than or equal to this threshold. Okay, and we call this threshold as t min. So here is our procedure here. At first, we obtain the t star by the formula that we had in the previous slide, and then we calculate t min, and then if t star is greater than or equal to t min, then we consider t star. That's it. But if it's not, we need to consider t min as our cycle time. Okay. And here we have an example 4.7 from the textbook. So please go through this example and try to solve it. And I will solve this example in our live session on Tuesday. Okay, so we are done. We are done on this lecture or chapter 4. So I'll solve this example in our live session. Also, I will have other examples in our live session. So please go through the lecture notes and the pre-recorded videos and have your questions in our live session on this Tuesday. Okay, thank you.